Hello and welcome to this M3 video on kinematics. On the screen is an M2 past exam paper question. Pause the video now if you would like to give this a go. At time t equals 0, a particle p is at the origin. That's telling us t equals 0 when x is equal to 0. And it's moving with speed 18 meters a second along the x-axis in the positive x direction. So v is equal to positive 18 as well. At time t seconds, the acceleration of p has magnitude 3 over root t plus 4 and is directed towards O. So if this particle is moving from the origin at time t0 in the positive x direction, the acceleration directed towards O means that this is a negative. That's very important that you get the correct direction on your acceleration. Part A, show that at time t seconds, the velocity of p is that expression there. Okay, here we've got A is equal to dv by dt, and we know that that is equal to minus 3 over root t plus 4, so we are going to integrate to get v is equal to the integral minus 3 t plus 4 to the minus a half dt. That will give us t plus 4 to the half, divide by that to get minus 6 plus c, and we know when t is equal to 0, v is equal to 18, so 18 is equal to minus 6, t is 0, so that's 4 to the half, plus c, 4 to the half is 2, so that's 12, and we get c is equal to 30. So v is equal to minus 6, t plus 4 to the half, plus 30, and that matches, although they've written their 30 in front, like so. Part A finished. Part B, find the distance of p from O when p comes to instantaneous rest. Okay, instantaneous rest happens when v is equal to 0, so I'll do that first. Let's find out when this happens. So we've got 30 divided by the 6 is 5, is equal to t plus 4, the square root of that, so 25 is equal to t plus 4, so this happens at t is equal to 21 seconds. Now we need to find the distance this happens, so we're going to be integrating again. X is equal to the integral of v dt, and we know v is 30 minus 6 t plus 4 to the half, so we're integrating this, and that gives us, with respect to t's, right? And that gives us 30t. This becomes t plus 4 to the 3 over 2, and divided by that gives us a minus 4 here, and a plus c. And we also know when t is 0, x is 0 from our original boundary conditions over here. So 0 is equal to 0 minus 4 times 4 to the 3 over 2 plus c. 4 to the 3 over 2 is 8, 4 8 is 32 is equal to c. So x is equal to 30t minus 4t plus 4 to the 3 over 2 plus 32. Now when t is equal to 21, go ahead and put that in. X is equal to 30 times 21, 630, minus 4 times 25, square rooted is 5, cubed is 125 times 4 is 500, plus your 32. Gives us a final answer of 162 meters for x. And there we go. In this video, we're going to be looking at acceleration varying with displacement instead of time. What we've done so far is used calculus to find displacement, velocity, and acceleration when they vary with time. So what we just did in the starter there, acceleration is dv by dt, and velocity is dx by dt. But you won't always get acceleration given in terms of time. or velocity given in terms of time. Sometimes it's more useful to have them varying with displacement. Simple example, if you consider a spring oscillating backwards and forwards, you know at the maximum extension of the spring you're going to have a change in direction. So while there will be a dependence on time involved in that, it might be more convenient to consider it as depending on displacement. In this section then, we're going to be doing pretty much the same thing as we've done in the previous video, but with a slightly different formula. Instead of this, we're going to be using v dv by dx. And this connects quite easily if you apply your chain rule. We know that a is dv by dt, and if we want dv by dx, then we have to times this by dx by dt, remembering that although these are not fractions, they kind of act a bit like fractions. Cancelling the dx's there brings you back to dv by dt. So using the chain rule, we can show that this is true, and of course dx by dt here is your v. So this becomes dv by dx times v, or more commonly written v dv by dx. And if you know what a is as a function of x, then you can write your a here, whatever that is, as a function of x, separate the variables as usual, bringing the dx up here, and integrate both sides. So you end up with the integral of v dv, which will always give you a half of v squared, and on the other side the integral of whatever your acceleration is as a function of x, integrated with respect to x, like so. And you might see this in your textbook, because this will always give you a half of v squared on the left hand side. Personally, I prefer to remember this, but it'll get you to the same place in the end. That's it on the notes. Here follow a number of examples and an exam question at the end to finish. Example number 1. A particle P is moving on the x-axis in the direction of x increasing. When the displacement of P from the origin is x, its speed is v, the acceleration P is 2x. Okay, that's the key point here. The acceleration is 2x, dependent on x, not t. When P is at O, that's x is equal to 0, its speed is 6. Find v in terms of x. So here we're using v dv by dx for a, and that is equal to 2x. Separate the variables and integrate. So on the left we've got what we expect each time we do this, and on the right whatever the integral is, in this case x squared. Now we've got our boundary conditions, we put that in. Half of 36 is 18, 0 plus c, so c is 18. So half v squared is equal to x squared plus 18. However, we don't want v squared, we want v in terms of x. So we should rearrange this now to give v as the square root of 2x squared plus 36. And because we know this is all happening in the direction of x increasing, we just need the positive square root here. That's the first example. Second example, a particle P is moving along the positive x-axis in the direction of x increasing. When OP equals x, the velocity of P is v, and the acceleration of P is this. Again, this is our key point here. A is equal to that thing there, which is also equal to v dv by dx. So if we have v dv on the left, we've got the integral of acceleration, which is 54x minus 3 minus 18x to the minus 5 dx, like so. There is a little caveat here that x is greater than or equal to 1, and we've got some boundary conditions here. Find v in terms of x. So on the left, as expected, a half v squared. On the right, that becomes a minus 2 minus 27. This becomes a minus 4, so that's plus 9 over 2 plus c. Put in our boundary conditions. When v is 6, That gives us 18 again on the left. And x is 1, so we've got minus 27 plus 9 over 2 plus c, and all of that gives us c is equal to 81 over 2. So we've got a half v squared is equal to minus 27x to the minus 2 plus 9 over 2x to the minus 4 plus 81 over 2. Again, rearranging to get v, not v squared or a half of v squared. I get v squared is equal to minus 54 over x squared plus 9 over x to the 4 plus 81. Now we need to square root this, but take a moment and realize that with x squared, x to the power 4 here and here in the denominators, this might factorize. And in this case it will. We can do 9 minus 3 over x squared, all squared. So then the square root of that becomes 9 minus 3 over x squared. Now a quick note on this. We know that this is okay because it says positive x-axis in the direction of x increasing, and if you use x is bigger than or equal to 1 in here, then the 3 over x squared is always going to be 3 or less. So 9 minus that will always be positive, that's fine. But in factorizing this, you could have had 3 over x squared minus 9. That would have worked as well. In which case, you would have had to take the negative root of that for this still to be true. That when x is greater than or equal to 1, you have a positive v. So whichever way your expression here ends up, you need to end up with a 9 minus 3 over x squared here in order to be consistent with the direction they've given you in the question. So when you square root things at the end of these questions, just make sure you know if you've got the positive root, the negative, or both. Next example. A particle p is moving along the x-axis. Initially p is at the origin and is moving with velocity 1 meter a second in the direction of x increasing. At time t seconds, p is x meters from O, has velocity v and acceleration magnitude this, directed towards O. So we're moving away from O because initially we're at the origin and we've got a velocity of 1, but the acceleration is directed towards O, so this is a negative acceleration. Here we've got a is equal to minus a half e to the minus x, and we know again that this is equal to v dv by dx. So on the left we're going to get a half v squared, and on the right the integral of minus a half e to the minus x dx, and integrating that we get a half e to the minus x plus c, and our boundary conditions, v is equal to 1 when x is equal to 0. So we've got a half on this side is equal to, that's a half as well. So c is equal to 0. So half v squared is equal to a half e to the minus x, and I'm aware I didn't actually read the question. I've just assumed what we're doing here. Find v in terms of x. Yes, that's what I was automatically doing for part A here. So as with the previous questions, we need v here, not v squared. So v squared is equal to e to the minus x, square root that, and we get e to the minus x over 2. Part B, make sure I read it this time. Find x in terms of t. So what we've been saying so far is that you can have acceleration and velocity dependent on displacement. But obviously you don't want displacement dependent upon displacement. That doesn't really make any sense. So when we find displacement in these questions, we're still going to find it in terms of t. So we're back to what we did in the previous video, using v is equal to dx by dt. So v is equal to dx by dt, and that is equal to e to the minus x over 2. The difference here is that our expression for v is in terms of x, so we're going to need to bring that on the other side, and dt will be by itself. So a very easy integral there, and whatever the expression is on this side to integrate gives us 2e to the x over 2 plus c is equal to t. Back to the question quickly for boundary conditions. initially, that's t is equal to 0, p is at the origin, x is equal to 0. So when t is equal to 0, x is equal to 0, and that gives us 2 plus c is equal to 0, so c is minus 2. 2e to the x over 2 minus 2 is equal to t. However, last thing on this, find x in terms of t, not t in terms of x. So we're going to need to rearrange this expression to get x equals. So a few stages of rearranging here. We've got 2e to the x over 2 is equal to t plus 2, and then divide it all by 2, and then our natural log, so x over 2 is equal to the log of t plus 2 over 2, and just times it by 2. T plus 2 over 2 like that. And that's the final answer for part B. Last example before the exam question. A particle P is moving along the positive x-axis again. At OP is equal to x, the velocity of P is v, and the acceleration is k over 2x plus 3 squared, where k is a constant directed away from O. So in this case, we're going away from O, which is where we're moving. So if I take that to be positive, we're okay. At x is equal to 1, v is 10, and at x is equal to 6, v is root 120. We've got two sets of boundary conditions because we're going to need to find the value of k and also c, our constant of integration. So doing the same as before, we've got a is equal to v dv by dx, and when we separate the variables, we get a half v squared is equal to the integral of k 2x plus 3 to the minus 2 dx. That's a linear expression, so I can just raise the power of the bracket by 1 and divide, so we get minus k, but I also need to divide by the differential of the expression inside the bracket, so that's 2x plus 3 minus 1 plus c half v squared. So I've got two things I don't know, but I've got two sets of boundary conditions. So we're going to put them both in, simultaneous equations, find our two unknowns. So v is equal to 10, that's 10 squared is 100, divided by 2 is 50 on the left. And on the right we've got x is equal to 1, so that's 2 plus 3 is 5, but that's minus 1, so that comes down, multiplies by the 2, so we've got minus k over 10 plus c. Our second expression, when v is equal to the root of 120, squaring that is 120, divided by 2 is 60, and on the right x is 6, so that's 12, 15, bring it down, combine it with the 2, is minus k over 30 plus c. To combine these, I'm going to change this into a minus 3k over 30, and then I can do this equation, subtract this equation to eliminate the c. So we've got 60 minus 50, 10 on the left, minus k over 30 minus 3k over 30 is 2k over 30, and the c is eliminated, so we've got k is equal to 150. Then if k is equal to 150, this equation becomes 60 equals minus 150 over 30 is 5, plus c, so c is 65. Now I didn't actually need that from what the question was asking me. Find the value of k, we finished part A there, but for part B I will need to know c, because to show that the speed of p cannot exceed root 130, I need to have a final expression for v here. So let me put this under part B, and then we've got a half v squared is equal to minus 150 over 2, so that's minus 75, 2x plus 3 to the minus 1, plus c, which is 65. Rearranging to show v squared, that's minus 150 over 2x plus 3 plus 130. So to get the maximum speed, let me maximize v squared first, and to do that we want x to be as big as possible. So this fraction is as small as possible because it's negative in the limit when x tends to infinity. This tends to 0, so v squared tends to 130. So as x tends to infinity, v squared tends to 130, therefore the maximum velocity is equal to the square root of 130. Last thing then is our exam question. A particle p moves along the x-axis. At time t equals 0, p passes through the origin, moving in the positive x direction. At time t seconds, the velocity is v, op is equal to x, the acceleration is this. Measured in the positive x direction, that's telling us that this is positive for our acceleration. Like so. Give a reason why the maximum speed of p occurs when x equals 30. Well, the maximum speed happens when the acceleration is 0. So let's put a 0 in there. And that gives x is equal to 30. Given that the maximum speed of p is 10, so that's telling us now, combined with what we've just said, the boundary conditions, x equals 30 when v is equal to 10. Find an expression for v squared in terms of x. So this one is just slightly different. We're finding v squared in terms of x, so we don't need to square root at the end of this. Everything else is the same. We've got a is equal to v dv by dx, and we've been given a in terms of x. So we can separate our variables and integrate. On the left we get a half v squared. On the right the integral of 5 over 2 minus x over 12. And that gives 5x over 2 minus x squared over 24 plus c for a half v squared. Now our boundary conditions, x is 30 when v is 10. So we've got 10 squared, 100 divided by 2 is 50 here. And then x is 30, so that's 75 here. Minus 900 over 24. Grab a calculator, and that gives 75 over 2. And if you do all of that, you get 25 over 2 for c. Putting it back in, a half v squared is equal to 5x over 2 minus x squared over 24 plus 25 over 2, and we want v squared, so all I need to do here is multiply everything by 2. 5x minus x squared over 12 plus 25, and that is our final answer for the exam question. That should be enough for you now to have a go at the questions in exercise 1b and the chapter 1 review exercise, and maybe I'll see you in the next chapter.